Hey everybody, and welcome to lesson 3, part 2 of circuits. Today we're going to continue to explore the same circuit demonstration with the same bulbs A, B, and C, but what we're going to find is that they behave very differently when set up. Okay everyone, so here again, same demonstration with bulbs A, B, and C, but we're going to mix things up a little bit. We are going to use the same battery, the same switch, the same bulbs, but we're going to have a different outcome this time, and in it we're going to look at what the differences are between two different types of circuits. So go ahead, flip that switch. I have it set up again. As you can see, in a basic circuit, a simple circuit is what we call it, with just a battery, a switch, and a bulb. Clearly A, B, and C, are not involved in this circuit, and hopefully just by looking and inspecting quickly, you can see why that is. Okay. Now, what I'm going to do is I'm going to take a piece of copper wire right here, and much like in the last demonstration with the series circuit, I'm going to place this copper wire so that bulb B lights up. But I'm going to place it a little bit differently. I'm going to take it, I'm going to put it here, ready, and I'm going to just drop it. Oop, oop. There you have it. Hopefully you already see what the difference is between the demonstration last time and this demonstration. There are actually two things, aren't there? One is this: bulb B is quite bright. Last time when I integrated bulb B in my circuit, when I put a potential difference across bulb B, it got dim. But here it's quite bright. And also, ready, let me push this off. Watch bulb A. Watch bulb A. There's no change in the brightness of bulb A. So this circuit is doing a really good job of producing power, right? It's doing a good job of producing energy as it relates to the rate of change of time, right? A lot of energy per unit time. Now bulb C, I'm going to do the same thing. I'm going to connect this here, I'm going to drop it down, and there we have it. Again, remove this quickly. Ready? Watch A and B. Nothing happens, right? And now bulb C is very, very bright. So A, B, and C are each creating a lot of power. They're generating a lot of power. They're dissipating a lot of power, as we like to say. And by integrating B and C in the circuit, we have not affected bulb A. So this raises a question, which is, unlike last time, why doesn't bulb A get dimmer when I add bulbs B and C to this circuit? And the answer to this aim is going to be related to the different way that I've connected the bulbs this time. Okay, and here's a little hint. Ready? I'm going to go ahead and I'm going to remove B, and we'll get back to this in a moment. I'm going to pull B out of the circuit. Let's see what happens to A and C. Nothing, right? A and C stay just as bright even when I pull B out of the circuit. Ask yourself, would that have happened with a series circuit? You should be able to answer it. So let's flip this circuit off, and let's go ahead and jump to the lesson. So where's my paper? Some of you may know that this type of circuit is what's referred to as a parallel circuit. Okay? Now, a parallel circuit is a circuit that has elements okay, that branch off from each other. And that branching that the parallel circuits do is really what is allowing for all of those bulbs in the demonstration to stay just as bright as the others. Now let me separate these. I'm going to draw my circuit on this page here so we can see it nice and big, because there's going to be quite a bit happening in my parallel circuit. Okay, so I'm going to draw my battery down here. And that battery is going to come out of my high potential, right? And it's going to go up here to a resistor, over, down, and back to the battery. Okay, I know I didn't draw that quite centered, but I hope the point gets across. Positive, negative, around to this resistor. And I'm going to name this resistor RA. That is resistor A. I'm also going to take a voltmeter, and I'm going to connect that voltmeter to my high and low potentials here, and it's going to tell us what the voltage of the source is. I'm going to take an ammeter, and I wish I would have drawn this in before, here. And this ammeter is going to measure the current. It's going to measure the current in this branch right here. Now, what I'm going to do that's a little different, a lot different actually than my series circuit, is I'm going to, at this point here, connect a wire that goes up like this and over to another resistor. And then back down. And I'm going to call this resistor RB. Then I'm going to do the same thing here. I'm going to go up to an RC, over and down. Okay, so I have my three resistors, RA, RB, and RC, connected with branches here and here. This is what I mean when I say branches. I'm referring to these dots where the thing splits into two. These are often referred to as junctions in the circuit. Then what I'm going to do is I'm going to take three more ammeters, and I'm going to place them here. Call that AA. This one AB, and this one AC. And normally what you would do is you would actually not draw the black line in the circuit like I did, but I just keep forgetting to draw in my ammeters. So when you draw these things, please make sure to leave a space and draw your ammeter in there. And I'm going to call this ammeter a total, because that's really measuring the total current in the circuit. Then voltmeters, right? I'm going to take a voltmeter here to measure the voltage across A, a voltmeter here to measure the voltage across B, and a voltmeter here to measure the voltage across C. So I have a lot of meters in this problem, right? Now, let's think back to the demonstration. In that demo, how did the brightness of these three bulbs compare? Well, they were equal, right? And I also know that the resistance of A is equal to the resistance of B is equal to the resistance of C. So all three resistors have equal resistance to each other, and they were all equally bright, right? Well, that certainly seems like they all had the same potential difference across them, right? Well, now the next thing is follow the path from the high potential of the battery to the resistor. Well, this is a conductor, right? This is a conducting wire. One thing that I think I mentioned before, but I just want to reiterate, is that the potential along a good conductor is pretty much the same at all points. One way to look at this is this. If I cover up B and C, this resistor is just a simple series circuit, isn't it? Battery to the resistor, back to the battery. If I cover up these two resistors, isn't RB in the same situation, right? Imagine these two, C and A, didn't exist. We're just going to have it from the high to the low. If A and B didn't exist, same thing. And so I can say that, like, if this is my positive end, like I said over here, well, then this is positive and this is positive. This is, I'm going to say high, 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 high potential, high potential, high potential, right? That's all high potential and the same high potential. Now over here, everything connected to the negative is the same. Negative, negative, or low, 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 right? Low, low, low. So it's all low potential on the right and all high potential on the left. As a result, each of these meters will read whatever the battery's potential difference is, because since these are all conductors going straight to the battery, it's basically just reading what the battery is. Even if I took those resistors away, right? VC is basically just connected directly to my battery. And so when we're talking about parallel circuits, if we want to talk about potential difference, right? I can say that the potential difference of the source is equal to the potential difference of 1, equal to the potential difference of 2, equal to the potential difference of 3. And that's my first equation for parallel circuits. The potential difference across each element in parallel with each other is equal to the other elements. And in this case, the battery is in parallel with the resistor A, parallel with the resistor B, parallel with resistor C. Now, the next part, which is a little bit more, I think, complicated to understand, but it's still, I think, straightforward enough, is the current. I'm going to use green to represent the current in order to just kind of make things a little clearer. We have a current coming out of this battery. I'm going to call the current coming out of the battery I total. Right? I total reaches this junction. Remember, current is charge over time. The charge over time, or the current, will split at this junction. Some of that current will go up, some of it will go to the right. I'll call this current IA. And I'll call this current here the current that goes through C and B. So IBC. Well, I think we can see if charge is conserved and we have charges or current going up to this junction splitting into two, the current that goes through A must equal, the current going through A plus the current that goes up through this branch here has to equal to the total current. Otherwise, what it's saying is when we reach this junction, we create current or we lose current. But conservation of charge tells us that can't be true. This is what's called Kirchhoff's junction rule. When you study more advanced circuits, you'll learn about it in more detail. And it really is just a statement of conservation of charge. What goes in must come out. Then IBC will break IB and then IC. And then it goes around. And here you can see, I had to stop the video for a moment so it didn't just magically appear. IC returns to this junction, and so does IB. And they recombine to form IBC again. Right? So IC equals IC, IB equals IB, IB plus IC equals IB plus IC, right? IBIC. Then here, IA passes through the resistor. You remember, I can say that this strand here is a series portion of the circuit. This is all in series, which means the current here equals the current here equals the current here equals the current here equals the current here, which means IA meets up again with IBC, and we have once again I total coming down. And so let's recall, every charge that comes out of a battery, for every charge that goes out of a battery, a charge goes into the battery, which means the current out of the battery has to be equal to the current into the battery. And that's exactly what we're seeing here, right? This total current is breaking up, recombining, and then coming back into the battery. And so if we go back to here, the current, we can see that the total current is equal to I1 plus I2, oh, I'm sorry, I should be using letters here, plus IB plus IC, and this should also be letters, right? Let's see how well I can make this work. Right, IA equals IA plus IB equals IC. All right, now, the last one will be our equivalent resistance, or REQ. Well, we're going to do this by looking at my current equation. My total current, I'm just going to jump straight to Ohm's law here, is the voltage of the source over the equivalent resistance of the circuit, right? Think back to that equation that we had in the last lesson, which was V source equals I total REQ. V equals IR, just Ohm's law restated for the system of the circuit. This is going to be equal to IA is, well, that's VA over RA, isn't it? Plus VB over RB plus VC over RC. And VS equals VA equals VB equals VC. That's what I have up here. Again, I lost my deltas, kind of just out of laziness, but it means the same thing. That means I can factor one of these out and cross them out and be left with 1 over REQ equals 1 over RA plus 1 over RB plus 1 over RC. And that leaves me with my final equation for parallel circuits, which is how to find the equivalent resistance of a parallel circuit. So I have my how to find the total current and how to find the potential difference. Those are my three big equations. All right. And so if I had these meters and I put them into the circuit, I should find these exact relationships. Just like with series circuits, I'd like to make it a gravitational analogy. If we take a look, I actually prefer to make the analogy to a volcano. Okay, so here I have a volcano that has lava or magma, whatever we want to call it, coming down out of it, right? It breaks into 3 different streams, 1, 2, and 3, okay? It starts at a distance of delta Vs, or a potential above the ground that's equal to this. Each river must then flow down that amount from the top of the mountain. Well, that means that river 1, river 2, and river 3 experience the same potential difference, don't they? They both drop from the top of the volcano to the bottom of the volcano. And then if we imagine a point up here, which is where like all the lava is coming out of, right? It's all the lava coming out of the top, and it may be magma, it may be lava. I never remember the difference. I'm not an earth science teacher, please forgive me, right? The sum of all of it is equal to the current in each individual path. And so the total current is the sum of I1 plus I2 plus I3. That's how I view parallel circuits, because it's very abstract. And so we need to kind of like have a analogy in order to understand what's really going on there. Okay, now that we have that, let's go ahead and work on an example. It's a little messy. Okay. So, battery going up and over, down. I'm going to connect this battery to an ammeter, A1, that goes through a resistor, R1, circles back to the battery. Right. Now I want you to notice, this is not a parallel circuit yet. This is just a circuit with a resistor, an ammeter, and a resistor. This is simply, did I say a battery? This is simply a basic, simple circuit. Now what I'm going to do is I'm going to extend it up like this, okay? I'm going to drop it down to a second ammeter, A2, and then to a resistor here, which I'll call R2. Notice, still a simple circuit, right? Just because I put this here doesn't change that, which tells us that potential has to be the same as the battery potential. All right, now what we're going to know in this problem is that I1, the current read by our ammeter 1, is 3 amps. The current read by ammeter 2 is 6 amps. And let's say that we know the resistance of R1 is 10 ohms. Again, normally I would give you a problem where I ask for a specific value, but what we're going to do is we're going to, again, make one of these vert tables, because we want to get practice solving for every possible thing we can. So resistor 1, 2, and total. And I did not leave myself enough space here. Hopefully I can get through it. So what do we know? We know current 1 is 3 amps. I know current 2 is 6 amps, right? And I know that R1 is 10 ohms. So first off, we know that the I total of a parallel circuit, right, if we put an ammeter here, will be I1 plus I2. I1 plus I2, well, that's going to give us 9 amps, isn't it? Then, well, I know I and R here, Ohm's law, V1 is equal to I1 R1, 3 times 10, 30 volts. Then this resistor is in parallel, with this resistor, which is in parallel with that battery, which means that this has to be 30 volts and this has to be 30 volts. And now this is just Ohm's law across the board, right? 30 times 6, 30 over 6, because it's R is equal to V over I, is equal to 5 ohms. Here, 30 over 9 is equal to 3.33 ohms. But what I taught you in this lesson was not how to use Ohm's law. It was how to calculate the resistance of a parallel circuit, or the total or equivalent resistance of a parallel circuit. To do that, 1 over R eq is equal to 1 over R 1 plus 1 over R2. 1 over REQ here is equal to, okay, 1 over R1 is going to be 1 over 10 ohms plus 1 over 5 ohms. Let's multiply this one by 2 over 2 in order to get a least common denominator. And so then 1 over REQ, I'm sorry, I know this is kind of sloppy, is equal to 3 over 10 ohms. But then we may ask ourselves, 3 over 10 is 0.3, it's not 3.33. Well, notice this is 1 over REQ, right? So then, this is getting even messier. REQ is going to be equal to 10 ohms over 3. Such a common mistake that students make, even students who really, really understand this stuff, is just forgetting to flip this when you solve. So you always have to be really, really careful to make sure to flip it, because this value is not equal to REQ, it's equal to 1 over REQ. Now, finding power becomes pretty simple, right? VI, that's going to be 90 watts. This will be 180 watts, and this will be 270 watts. And just to confirm that our answers are right, 180 plus 90 equals the total power, or 270 watts. Okay, so again, I got interrupted, so this is going to be about take 30 of this particular video, or this portion of the video. Overall, it's been about 30 takes of the video, whatever point I had to stop and continue. So I have my 3 bulbs here. I'm going to flip my switch on, and so here immediately we can tell that this is a parallel circuit because the bulbs are very bright and they're all equally lit. Now, of course, if it was a series circuit, they'd still be equally bright, but they'd be much dimmer because the resistance of the circuit is quite a bit larger than for a parallel circuit, and therefore the current in this circuit is higher. In a series it would be lower, and so the bulbs are brighter and there's a greater power dissipated by the circuit. Now, what I want to do quickly is, like, this circuit here is kind of messy and confusing looking, and I don't expect anybody to look at this and immediately know what's going on because there's a lot happening. In the circuit diagram that I drew below, it's a little bit clearer, but what I want to do is show you how this circuit is the same as the circuit that I have drawn over here. So high potential, over to here, over to here, over to here. Recall, I don't remember if it was this lesson or the last, but conductors, oh, it was this one. Conductors that are connected to each other have the same potential. So this is the high potential, this is the high potential, high potential, high potential. Are we getting ready for take 90 now? There we go. High potential, high potential, high potential, high potential, high potential, high potential. So all the casings of these bulbs, like these portions of the bulbs are at the high potential. All of these portions, the bottom portions, are connected to this metal, which is connected to here, which is the low potential. And so we have high potential, low potential, all the branching, right? Current comes through here. The current has to go one of two ways, down or over, and it can do both, so it branches, right? Branches and branches and branches, getting to the low potential. So it's a parallel circuit. Something that's really convenient about a parallel circuit is that you can have one of these bulbs go out or be disconnected and still have the circuit run. For example, I'm going to take this one and I'm going to pull it off. B has gone out of the circuit because I've removed the wire connecting it to the low, and yet the bulbs A and C are still connected. They're still receiving a potential difference, right? Put it back and they're bright. That's very different than, let me set up my series circuit. Setting it up, needed to go through there, to here, to here, to here, up to there, to there, to there, to there, to there. I think this should work. I'm not quite sure why it's not. Let's see. There we go. Okay. So, see, when this wire is on here, okay, when it's on here, rather than go up through this nasty bulb and resistor, both of them actually, it can just go through this wire, so it chooses to do that. Remove this. They're all equally bright, but like I said before, dimmer because the current has gone down. If I remove B from the circuit, ready? They all go out. So this may remind you of holiday lights, Christmas lights, whatever you want to call them, or the old style, right? If anybody remembers when one would pop, they all go out. Some of you may still have some, and then you have to throw the strand out or locate the one that's out, and it's a real pain in the neck. Well, by designing them to be in parallel rather than in series, just like this, This creates the bulb so that one can go out and the whole strand doesn't go out. And then you can easily identify which one popped and replace that bulb. Okay, so that's one of the benefits of parallel over series. You know, if you go in your kitchen or your living room and you look at the lights above when you turn the switch on, if one of those bulbs goes out, does your whole living room go dark? No, right? So you can kind of infer from that what the electricians must have wired, or how your electricians must have wired those lights together, right? They had to have been in parallel. Okay, so that is it for our parallel lesson. We will have one final lesson this week related to circuits, and that lesson is going to be about power consumed by a parallel circuit and a series circuit. It is nothing new from what you've learned. It's just sort of tying things together, and it's a good example to explain what's going on.